Hello everyone, welcome back to our about the PDEs lectures. So today we're going to talk about the boundary conditions. So recall from the previous lectures. In the previous lectures, we were assuming we have the one-dimensional rod and using our basic knowledge of physics and chemistry and some properties of fluids to conceptually understand what's going on there, and from the conceptually to create our partial differential equation from conceptually to construct our equation. And since we were dealing some after constructing it, we realized that we having two unknown functions, and even going deeper through, we come up the PDEs that only we have one unknown functions with only one unknown, which is our temperature. Now, in the ordinary differential equations, when we solve the differential equations using the different methods, we always without the initial conditions, we could still able to solve our ordinary differential equations. However, unlike the ordinary differential equations, partial differential equations are very difficult and requires, you can solve it without the initial conditions, but you need another conditions in order able to solve it, and that's called the boundary conditions. So what does boundary conditions is the conditions that occurs at the boundaries. So to solve our temperature from this heat equation, we need to know what's happening at the temperature around the boundaries. What's happening right here. So we're going to start with called prescribed temperature. The prescribed temperature is the temperature of the end of rod. So let's say we are looking at x, the position when x is equal to. So it's the temperature of the, and we're using our approximation saying the temperature right there, 0 T, is defined like, let's say, UB of T. So suppose we put our one-dimensional rod in a fluid bath, right? And so there's a temperature differences. Let's say the fluid has a higher temperature than a one-dimensional rod. So the boundary is the one and this boundary. At this boundary, our temperature, we can approximate it using the temperature of our fluid, whatever fluid we have here, that our rod is contacted. And that temperature is our U sub B of T, and which is the UBT is the temperature what's going on of the fluid bath with which the rod, let's say, is contacted. So here, this is the example boundary condition where only our temperatures is given. But there will be a condition where it's not only the temperature, it's the heat flux. The heat flux is given. Let's call this as an insulated boundary. So before I put the equation, let's understand conceptually what's going on. So here, as soon as there's a temperature differences, I put my one-dimensional rod there. So therefore, from at this position, there will be heat flux we're gonna follow. Because the heat flux, how we know there's a heat flux? Because at the boundary that it's contacted with, that our rod is contacted with the fluid, due to its difference of temperature, the temperature right inside should increase as well. So there will be the heat flow across the boundary must be occur in order to increase the temperature in the center as well. So we can also have a type of boundary conditions where only like we can say our heat flux is given. So we can use like our Fourier's law of the heat conduction. Let's say our heat flux at that time is given as negative K naught at that position, partial U, partial X, at that X equal to 0 T. This is the given. Based on this, you can determine how pure conductor or how good conductor can be initially. Now, for the simplest boundary condition which is easier to solve our PDE, simplest boundary condition is the perfectly insulated. So perfectly insulated, meaning that there's no heat flow across the boundary. So therefore, I can say at that position, my partial U, partial X, 0T, at that position, at that given time, is equal to 0. So there's no heat flow. So it's insulated, perfectly insulated. So this is a type of boundary conditions that you might expect to have for your given PDEs to solve it. Now, let's say there's another topic that you might have seen a lot especially in algebra, and you might solve that equation in a ordinary differential equations, or you have seen in a calculus. The one thing I'm talking about is the Newton's law of cooling. Newton's law of cooling. So, when a one-dimensional rod is in contact with boundary with a moving fluid, we have a moving fluid. Neither the prescribed temperature nor the prescribed heat flow can be appropriate to solve it. Like for example, the warm rod is contacted with the colder moving air. So definitely, if we say like example, we have the the warm rod in contacted with cooler moving cooling air. So the heat will leave the rod using the zero law of the thermodynamics. The heat will fall from the rod to the our air, to the fluid, which cause to increase the kinetic energy of the air molecules. In other words, to heating up the air, and therefore then the heat that's the closest at the boundaries of our rod will heat it up, and therefore the air molecules will collide to the neighboring air molecules to transfer the transfer kinetic energy from one molecule to the another in order to heat it up and transfer the heat, and that's called a convection. And air will then carry heat away, and that's called convection. Okay, So as I expected, like you can do this experiment by yourself. If the rod, even though it interacted with the cool moving air, still, if you put your hands closer to the rod, the air will feel the warmer. The farther it is, the cooler it is. So the smaller of the energy transfers to the neighboring of the air molecule. So now, so we can say that our heat flow is inversely related to the distance. The farther it goes, the cooler the air is. But experimentally, the the heat flow that's leaving the rod is directly related, is proportional to the temperature difference between the bar and the prescribed external temperature. Now, what would be the boundary condition for this given scenario? The boundary condition is our Newton's cooling law, where our heat flow negative at that boundary. Sorry, not x, not t with heat flux, not the here the heat flow per unit of time is equal to negative h of u of 0t minus ub of t. Okay, so now you might ask, what's our h? H is our proportionality constant, which I will talk about right now. So for right now, there's one question is, what the heck, why I put the negative sign here? So the negative sign is because of this scenario. I put a negative sign. Let me explain why. Since we talked about the warm rod is contacted with cooler moving air, so we expect the heat flow to move out through this direction. So we expect the temperature at my boundary, like let's say this infinitely small, this boundary is greater than the similar boundary I will draw it here, that are outside of the rod. Than the outside of the rod. So my h is, even though my h is the the proportional constant, it has a term. It's called the heat transfer coefficient. It's also, you can call it as a convection coefficient. Convection of the coefficient. Now, because of my heat flow is going from the rod to the outside, so the heat within the rod, our heat flux is negative. It's leaving outside. So the temperature difference we expect to be negative. So therefore we put this negative sign. So let me restart it again. I apologize. So since at that boundary, the heat is flowing out the rod, it's flowing out the rod, it's flowing out the rod. So therefore our heat flux, partial U, partial X, we expect to be negative. And then from the Fourier's law, this entire thing is going to be positive. Now, since our temperature difference is going from the inside to the outside, definitely we will expect that to be a negative at that boundary. And therefore we multiply our negative sign. We have the negative sign to make it equivalent. To make it equivalent. Now let's look, since we're looking at this position, now let's look at this position at x equal to L. Now, our boundary condition, using the same scenario, now we are looking but for x is equal to L. Now, so let's again look at it. Let's construct. So we understand how we come up with this. Now let's look at this position. Let's understand what's going on. At this position, so we expect the rod is going from the rod, the heat is transferring from the rod to the air. So again, our heat flux is moving to the right. So the temperature as it goes to the right should increase. So therefore, our partial U with respect to x is positive. So therefore, if we construct our equation, now we're looking at x equal to L, partial U, partial x, L T, that's equal to H times U of L of T minus U of our UBT. Which is pretty similar as this, to this, except our negative sign. So you have to be careful when you assign your negative signs or not. Now, one thing you might notice when we apply Newton's law of the cooling, if you notice, our boundary condition contains both the derivative of the other unknown and the unknown itself in just one simple equation. So therefore the boundary condition is not just our function with itself or the derivative itself, it also can contain the combination of itself as well. Now for the interest, now we'll continue to talk about the H, the meaning of the H. Therefore, all the proportionality constants in equations that determine is the term that depends on the type of the material is determined experimentally. Now, everything that I will talk about is experimentally, and then you will see mathematically here why that makes sense. Now, if our H is small, very, very small, therefore, we expect very little heat energy flows across the boundary. So if I do the Newton's lawing approach for insulated boundary conditions, if I take the limit for the age approaches to 0, the Newton's law of cooling boundary condition for insulated it approaches to the Newton's laws of cooling of the boundary conditions that is completely insulated, which makes sense. Why? Because if my age is 0, this entire thing will become a 0, and that's true if this is equal to 0, and therefore this left with equal to 0. And if you remember here that I mentioned it, for the simplest boundary condition, the perfectly insulated is this, because there's no heat flow across that boundary, so we expect it to be insulated. Now, for age that is not equal to 0, therefore it represents the Newton's law of cooling as an, let's say, not insulated boundary, but not perfectly, like imperfectly insulated boundary. And then if my age is extremely large, therefore therefore the boundary condition is approaches to the prescribed temperature. In other words, my U is equal to T, like here. So let me just write it here. Partial U partial X is equal to 0. So you can summarize all of this type of boundary condition within this based on our proportion. Now, you might ask, why is this true? I will just do simple mathematical one step, and you will realize why it does make sense. Let me just rewrite my, let's say, doesn't matter which one, at x equal to L or x equal to 0. I'll write at x equal to L. So at k0 of L, partial U, partial X of L comma T, that's a positive H of U of LT minus U at bath T. Now, if I divide both sides from L, it's not L, H, so partial X is equal to U of L comma T minus U of B T. Now in the limit and then I take limit as H approaches 0 of this entire thing. Therefore, it leads me that my U of 0T is equal to U of B of T. Okay, so, sorry, not 0, I apologize, infinity. Oops, minor mistake. Okay, so this is at the conditions that we are looking when we put the rod within a fluid that is what's called there's a temperature differences within a fluid and a rod, and you expect a heat flow. Now let's say we are in equilibrium. Let's say equilibrium temperature distribution. So we're gonna start with, again, prescribed temperature. What we expect is our prescribed temperature and then insulated boundary, and then combine them, what kind of theory that will come up with. So now, if our thermal coefficient are constant and there are no sources of thermal energy, so that's when there's no temperature differences, so you expect that no heat flow, no thermal energy flow, then the temperature, so that the temperature will satisfy our PDs. Let me just write that scenario, that will be easier for what did I just say. If the thermal coefficient are constant and we don't have no sources of thermal energy, so we expect like so in other words, this Q is zero, this Q is zero, and all of these things are constant. So therefore temperature of that one-dimensional rod satisfy these given PDEs. Which the K, if you remember, is the K naught divided by 0, which explains the diffusivity. So suppose now we describe our boundary conditions. Now our let's say we have an initial condition where at time 0 our temperature has the following formation. It can be periodic, it can be like some Taylor series thing, and just a type of function. And our solution of that PD must satisfy this initial condition as well. But the initial condition, as I said, is the last step that we have to worry about. The first thing we have to worry about is solving the PDEs is the boundary conditions. Now, it's also the boundary conditions must be such that we have at 0t, at the x equal to 0, one end, it's defined as the temperature of time t, and then on the other end, we define as t2, comma t. And then we can also use the steady state condition. We have to talk about the steady state condition. In the steady state conditions is the condition where the boundary condition is independent of the time. Steady state condition is when the boundary condition is independent of time. So meaning my partial u partial t is equal to 0. So later when we solve the boundary condition, you will see the time dependence part of my solution. If I approaches to infinity, the time approaches to infinity, it becomes the steady state. So my temperature is not changing at all at that far away time. So it does make sense, right? Because when you put in a temperature difference, it's constant, the heat flows until you reach at the equilibrium. At that equilibrium, there's no temperature changes, there's no heat flow at all, right? So that it reaches that given time where there's no heat change in temperature reaches. So that means our temperature is not the time dependence at all. And that condition is called a steady state condition. Steady state condition, which is also helpful to use to solve our PDEs. Now, let's go to the insulated boundaries. In our insulated boundaries, we have all the types of PDEs are consist of the PDE equation, the boundary condition, and the initial condition. So our PDEs we're gonna rewrite as partial u partial t, that's equal to k times partial u partial x squared. Now my boundary conditions are that my partial u at 0 comma t is equal to 0, and partial u partial x of lt is equal to 0. So we are at the equilibrium, there's no heat flow, but there's still some temperature differences at one end and the other end. And my initial condition, let's say at time 0, my temperature varies given with this function f of x. Now, using this, let's try to solve it. So now at the equilibrium, temperature distribution, at the equilibrium temperature distribution, there's equilibrium, there's no heat flow at all. Our flux, there's no heat flow at all. So we must expect, so it reaches to its steady state. So we expect, since at steady state there's no time dependence, which is 0. Therefore, our term is also 0. So I can say, since at steady state, it's like a steady state, there's no time dependence. Therefore, my partial becomes the ordinary. X squared is equal to 0. Now, from here, I know that my u is the equation of the line, right? And I can write that as my u is equal to c1x plus c2. Now, to solve those constants, I just have to satisfy to its boundary conditions, right? And my boundary conditions is given in this derivative form. This is my boundary conditions. Now, let's find the partial u. Now, my partial u partial x, which is equal to my partial x of c1x plus c2, that one will be equal to c1. Now, since at x equal to L, now at x equal to 0 or x equal to L, where the partial u of x is equal to 0, therefore my c1 is equal to 0. And therefore, my temperature is just equal to constant c2. Now, this constant can be any constant at all. So therefore, we can say that there is not a unique solution. And there is no unique solution. Any constant temperature is an equilibrium temperature distribution for an insulated boundary condition. So if we're using the time, so for the time dependence initial value problem, right? We expect that if T approaches to infinity for my temperature, it becomes my C2. C2. Now, if you want a long enough rod with insulated ends, the insulated end should approach the constant temperature. And this is reasonable, but it doesn't make sense that solution should approach the arbitrary constant. So because this lack of uniqueness was caused by the complete neglect of the initial condition. So this is because in general the equilibrium solutions doesn't satisfy our initial conditions, because the particle constant equilibrium solution is determined by considering the initial condition for time-dependent problem. So since our both ends are insulated, the total thermal energy is constant. Now, therefore, since we're talking about the long enough, if I follow the conserved thermal energy for the entire rod, so if I follow not the conservation of thermal energy of the entire rod, but the integral conservation thermal energy of entire rod, so if I write my d dt going the integral from 0 to L, which is equal to negative k0 partial u partial x 0t plus k0 partial u partial x at the L of t. Now, since both ends are insulated, we expect dt of the 0 to L u dx should be equal to 0. Therefore, my integral 0 to L 0 u dx must be equal to a constant. Implication is that the initial thermal energy must be equal to the final thermal energy. Which is the conservation of energy. So our initial thermal energy for the entire rod was described by given the initial condition going from 0 to L 0 f of x dx, which is our initial condition. Now, if I equalize this, and since u of x0 is equal to f of x, well, now the thermal energy sorry, not the thermal, but equilibrium thermal energy. So we got our U is equal to C2, an arbitrary constant. So therefore, I will just substitute, instead of U, I will just put my constant C2 dx. All of these thermal coefficient things are constant. So therefore, if I integrate it, my integral will be equal to 0 C2 times L. Now I will equalize it to, this is my final, at time approaches infinity. This is my initial. So therefore, if I equalize them together, I will get the 0 integral 0 to L f of x dx is equal to 0 C2 times L. Therefore, my C2 is equal to 1 over L times the integral 0 to L f of x dx. At these positions, my constants just get cancelled, and I divide out. And since I prove it here that U is just equal to my bound arbitrary constant, therefore my function U, the solution, is equal to 1 over L integral from 0 to L f of x dx. Okay, I know I've said a lot. I will just refresh what I just said, and we are done, because this is all about these types of the boundary conditions. Okay, so at the equilibrium temperature distributions, we know that our rod reaches to equilibrium, meaning there's no heat flow at all. The heat flow at all. So now we expect our condition, and we are considering all the thermal coefficients are constant, and there are no sources of thermal energy at all. So we have this equation. Right here. So now because we give an initial condition, which is only last step to worry about, and we have the boundary conditions that we have to worry. And there is this condition called the steady state condition, where boundary condition is independent of the time. So in our insulated boundaries, there is no heat flow we observe at all. Right? One end is this temperature, the other end is that temperature, and therefore we expect, but since there's no heat flow at all, it reaches to its thermal equilibrium. So we expect that there's no heat flow, so at the boundary, the heat must be equal to 0. And we given the temperature, how the temperature is distributed initially with the function of f of x. Now, since it's at the steady state condition, there's no time dependence at all, so this is equal to 0. Therefore, my derivatives is also equal to 0. As it equal to 0, now solving, we got the two constants to solve for. We can apply the boundary conditions. Applying boundary conditions, we only understand that our C1 is equal to 0. But it doesn't help us to solve for C2. So C2 is just the arbitrary constant, which shows that there is not unique solution, which concludes that boundary condition is not enough to solve our PDEs. So we need the initial condition in order to solve it. Now, because we got this arbitrary constant, we expect that at the long enough after it's reaching up, when we put in different temperature differences in fluid, they contact it until they reach the thermal equilibrium, there's no heat flow at all. We expect that our temperature should be equal to our arbitrary constant. Now, how are we going to find the arbitrary constant? We must have to solve it applying our initial condition. So for initial condition, we want to say it's f of x. But wait, no, that's a time equal to 0. Time equal to 0. And if you realize, now if I apply integral conservation of thermal energy of the entire rod to get what my temperature is, I will see that my time dependence is, since its time dependence is equal to 0, therefore my integrand is also equal to a constant. Now, because of my initial thermal energy, I can substitute my u into f of x. My u to f of x. Now, I have this. Now, at the equilibrium, I have my u equal to c2. And since all of these constant, this integral becomes this. And therefore, I equal them together and solve for my constant, and I got this expression. And if you notice, this expression is just the average of my f of x over the entire rod, average the temperature of the entire rod. The average of this entire rod. So this is it. This is all about our boundary conditions. The next lecture is we're going to derive our heat equation in a 2 and 3 dimension. Thank you so much for listening. Have a wonderful day, and I will post my lecture notes on my Instagram account. Have a nice day.